This is the last video for chapter 24. We're going to be looking at Gauss's law in situations where there's spherical symmetry. Now remember, Gauss's law says that the total flux through a surface is equal or is proportional to the charge enclosed inside that surface. And what we mean by spherical symmetry is that we can rotate the system in any direction around any of the three axes, and the system looks the same. It's called spherical symmetry because if you take a sphere and you rotate it any way you want, it's still going to look the same. And not surprisingly, the Gaussian surface will be a sphere. Very basic example of this is a point charge, but this will work for any charge distribution where the charge density rho is a function of the radius. Rho here is the volume charge density, which is charge per unit volume. And you have one problem in your homework, 41, where rho is not constant, where rho actually changes with the radius. And I'll give you some tips on how to work that after I've done an example. But most of the time, rho is constant. So if rho is constant, rho equals the total charge over the total volume. And you'll need to remember a few important examples, or a few important equations. The surface area of a sphere is equal to 4 pi r squared, and the volume of a sphere is equal to 4/3 pi r cubed. And you may have noticed that if you take the derivative of the volume of the sphere with respect to radius, you get the surface area, which is kind of interesting. If you can figure out why that is, you will go a long way to understanding how these three-dimensional integrals work. And the best way to do this is jump right into an example. Problem 37. Rutherford's model of the atom, you have a nucleus with charge plus Ze, where E is the electron charge, and Z is the atomic number. And then around that, there is negative Ze evenly spread throughout this volume R. And we want to find the electric field inside the atom. Now notice that the electric field outside the atom is going to be 0, because if you draw a Gaussian surface outside the atom, the total enclosed charge will be 0, because you've got the positive Ze and the negative Ze, and that adds to 0. And that means that we're looking for E as a function of R, and when we put the electric field in for capital R, it should equal 0. So that'll be a way to check our work when we're done, is do we get 0 field when we're right on the edge of the atom? But what we'll do is we'll draw our Gaussian surface of radius little r that is less than big R, centered on the nucleus. And because this system has spherical symmetry, the electric field is the same at every point along our Gaussian surface. And so our flux, E dot dA, just equals E times the integral of dA. The integral of dA is just the surface area of that sphere, which is 4 pi r squared. And now we need to figure out what the enclosed charge is, and that's typically the most difficult part of these problems. So first off, we have plus Ze, but we've also got some of the electron charge. And if we say that the charge density in this sphere here is rho, So ZE plus the enclosed charge density times the volume. Now that's helpful, but we still need to express what that charge density is. And it equals the total negative charge, which is negative ZE, divided by the total volume of the atom, which is 4/3 pi times big R cubed. But notice this is the volume enclosed by the Gaussian surface. And so that volume is equal to 4/3 pi times little r cubed. And that means the enclosed charge, you got plus ZE, but rho is all this. And if we do some algebra, and you should work through all the details yourself, we end up with this expression for the enclosed charge. And now I'm out of room, so we'll make a new slide. So we've just determined that the charge enclosed in our Gaussian surface, I'm going to rewrite it a little bit, is given like that. And we know that Gauss's law says that the integral of E dot dA equals that enclosed charge over epsilon 0. But remember, we also said because of the spherical symmetry that E is the same at every point on the Gaussian surface. So our E dot dA turned into E times 4 pi r squared. And that equals that. And now we divide by 4 pi r squared, and we find that the electric field is 1 over 4 pi epsilon 0, remember that's just Coulomb's constant, times ZE over r squared times 1 minus r cubed over big R cubed. And that is our answer. Now, to check that, we'll set little r equal to big R, and we'll make sure that E equals 0. And if we do that, we find that if little r is equal to big R, this fraction becomes 1. 1 minus 1 is 0. And so that checks out. Our answer is at least not wrong. Or it's probably correct. At least it fits that particular check. Now in that problem, the charge density of the inside the atom was constant everywhere. So rho was the same value. And so to get the total enclosed charge, you could just do that charge density times the enclosed volume. But you've got one problem on your homework assignment, 41, where the charge density is not constant. And in that one, I think your charge density equals rho s, which is a constant, times little r over big R, where big R is a constant. So rho is a function. And you need to find the electric field. And finding the enclosed charge in this case, what you'll do is you've got the overall charge distribution has a radius capital R. And when you draw a Gaussian surface of radius little r, you want to know how much charge is enclosed in there. And not surprisingly, our general expression for Q is rho times V. But if rho is not constant, that's going to be written as the integral of rho with respect to V. And so what we need to do is figure out what this dV is. dV is a small volume element. And within that small volume element, rho should be the same everywhere. So what we'll do is we'll pick our volume elements to be a series of very, very thin spherical shells of radius r and thickness dr. So all that is dV. The reason we do that is because charge density is a function of radius. And so since every point inside dV has the same radius, every point within dV will have the same charge density. And now we need to figure out what the volume of dV is. And you can think of it as a very flat surface that is formed into a sphere. That flat surface has an area of 4 pi r squared and a thickness of dr. So for a flat, pancake sort of shape, the area is, or the volume is the area times the thickness. The area is 4 pi r squared. The thickness is dr. And so the result is that the enclosed charge is the integral of rho, which is a function of r, times 4 pi r squared dr. And you'll integrate from 0 out to whatever radius you're interested in. If you're trying to find the total charge inside this distribution, you'll integrate to big R. If you're interested in finding the total charge within a smaller part, you'll integrate to little r. So that will be a nice fun challenge for you. But tomorrow I'm going to be checking questions 8 through 10. I would recommend that you do those before you attempt 41.